This is a pretty challenging trig identity that would take a while to expand and substitute, and it is true. But sometimes an identity, by doing all the substitutions, you can prove it to be true, but it doesn't give a real insight into it, and that's where a geometrical, or sometimes called a proof without words, proof is just better, easier, and gives you some insight. I want to show you what the proof without words looks like for this complicated identity. Now, this is a proof without words, as they say here. And when we look at this, we see there's a lot of right triangles in this picture. And this identity resembles like an a squared plus b squared equals c squared. So if this is theta, and the radius of this circle is 1, we have from our picture from previous time with tan, sine, cosine, and secant. Now, sometimes we have this other triangle, up here, which has cotangent and cosecant in it. But we could also move that triangle down here. So that means this is cotan and this is cosecant. The fact is that this angle and this angle are both 90 minus theta. So the tangent, and this is 1, so the tangent is going to be of that 90 minus theta is cotan, and the secant is cosecant. So now if we look at this giant triangle, this proof is finished, because this green side here, green side, is tan theta plus 1, and this blue side is cotan theta plus 1, and this big diagonal, which I'll make yellow, is cosecant plus secant. So because of that triangle, we have tan theta plus 1 squared plus cotan theta plus 1 squared equals secant. So that's an example of how a proof without words can give more of an insight than an algebraic identity proof. Today's lesson was about sine and cosine curves. So here's a graph of y equals sine x. And this classic sort of sine curve, where the x value is the angle, I put it in degrees, and the y value is the sine of that angle. And this means that, for instance, there's a point here at 30 comma half, and a point here at 45 comma square root 2 over 2. And we can see some things in this picture. For instance, we can see that sine is positive when x is between 0 and 90. It's also positive between 90 and 180. It's negative between 180 and 270, and also from 270 to 360. These are the same things that we got out of the unit circle, where the sine was the y coordinate. There are some things that you can see when sine is thought of as the y coordinates of this sine curve. I'm making red right now. Make it somehow easier to see certain properties. For instance, if here's like some sort of angle, theta, we can see that if I make a horizontal line, this angle here, whatever this is, has the same y coordinate, and we can see that it's 180 minus theta, because here's 180 here, and if I go sort of backwards to symmetry, so like that's theta and that's theta, and I could also make down here a horizontal line, and we can see this would be theta, this would be theta, so this angle here would be 360 minus theta. Can I change these thetas to alphas? I think it will be better for our purposes. And over here, this angle here is 180 plus alpha. Basically, it shows us how the reference angle is related to the three other angles that have that as its reference angle. I want to show you a little activity of why the sine curve looks like that. So here's the way this activity works. I have this circle here with 10 degrees slices, and if I take this 10-degree line here and I sort of take this length here, which is this red vertical line is sine, and I put it right here, and then I go over to the 20-degree line and make this vertical line here at the 20 degrees. Here it is in blue. And I move that over here. And I take the 30-degree line. I'll make it green. As you can see, it's getting bigger, and it looks like it might be coming like a straight line, like if I connect these. But it's not going to become a straight line. But I think somewhat surprisingly, here's the 40-degree line. I transfer it over here. It wouldn't be that surprising if it became a perfect semicircle, but it doesn't become that either. What ends up happening when you copy all these line segments, I just go from the y-coordinate and go down to the horizontal, that radius there. After 90, it starts getting smaller to become these lines, and after 180, it starts becoming, like at 190, becomes negative because it's going down, and that becomes these lines. And in doing so, we don't get two perfect semicircles, although it wouldn't be that surprising if we did, but instead we get the classic sine curve shape. A question to ponder is why don't we get perfect semicircles? And that answer has something to do with the fact that if I make these vertical lines, the sort of spacing between how far apart the vertical lines are is not, it changes. But over here, the spacing is exactly the same between every 10-degree slice. Now for the cosine curve, we do something similar, but the cosine is the x-coordinate. So cosine of 10 is this length here. It's going horizontally, but I'm going to make it vertical on this grid. And if I go to cosine 20, I go horizontally from this 20 degree sort of radius of 20 degrees towards the sort of vertical diameter. And it gets smaller. And if we keep going on that, 30 degrees gets even smaller. And what ends up happening here, once I get to 90, it's just 0. But then what happens is that at 100, we start going in this direction. It's small, but it's going to the left will make that negative, so it starts going under. And what will end up happening is we'll end up getting something like this. And that's our classic cosine curve. So that's a little activity that you do with an index card. Basically, we're transferring the horizontal lines to become vertical lines on this picture, and this becomes y equals cosine x. This becomes y equals sine x. You might notice that the cosine curve is kind of a piece. If you start the sine curve over here and you continue, it becomes the cosine curve because of all the symmetry that goes on with these vertical lines in this picture and the vertical lines on this circle and the horizontal lines on that circle. Cosine starts at its highest value. It goes down to 0, and then it becomes negative for a while in these two quadrants, and then it becomes... So in these two pictures, we can see things like we can see that sine is positive in quadrants 1 and 2 and negative in quadrants 3 and 4. We can see that cosine is positive, then negative, then positive. And because of the symmetry, we can see various other things like if this is theta, I'm going to continue it this way also at negative, as negative theta would be here, and we can see that for cosine is the y-coordinate. For this picture, the sine is the y-coordinate. For this picture, cosine is the x-coordinate. So these graphs don't have as much information individually as the unit circle has. The unit circle has, every point has like an angle associated with it and an x and a y coordinate, which are the cosine and the sine, whereas these graphs have less information. It just has its angle here and the y coordinate. In this case is cosine, and in this one the y coordinate for this picture is the sine. But we can see that cosine of negative theta is equal to cosine theta because of this cosine curve would have symmetry over the y-axis. But for sine, it would continue this way. It would have symmetry over the origin. So we can see on this picture that sine of negative theta, here's theta, would be not the same as sine theta, would be negative. So there are certain things you can see when the graphs of the sine and cosine are sort of separated from each other instead of all being together in the unit circle.